Welcome everyone. I'm R Emonet and I'm from Recalibrate Laboratory in Saint-Étienne, France, and today I'll be teaching you about uncertainty quantification and what we call Bayesian neural networks. So let's start right away. What we'll cover is what is basically the uncertainty we are caring about, and what are the traditional machine learning and deep learning approaches, including Bayesian neural networks, to handle this uncertainty, so to quantify it and to maybe mitigate for it. So I don't think I need a lot of time to explain to you how uncertainty can be important in decision making, but if you give an automated system, which are more and more present today, to an expert, the first thing the expert will be doing is thinking, can I trust the predictions that are made? So are they actually accurate? But the second question will be how confident the system is in its prediction. So how much can I trust a given prediction to be actually correct? And another question, which is the subject of another session in this call, is actually how the decision was taken by the system. And this is all about interpretability, but I won't cover this section here. So uncertainty is very important as soon as you have a decision-making process that is slightly complex. For example, when you do a medical diagnosis or things like this, you have some asymmetric costs where making an error in one direction, like not treating a patient, can be very different in terms of impact and costs than making the opposite decision, so not treating the patient while it's important. And this obviously depends on the treatment that we are considering. So as soon as a situation is uncertain and the costs are asymmetric in some sense, so the decision-making process involves benefit-risk balance, basically, then it becomes critical to have a good assessment of the uncertainty of a prediction given by a model or even by an expert. So we'll now switch to thinking about uncertainty itself and how it can be manifesting in different systems. So if I take the Wikipedia definition, uncertainty is about imperfect or unknown information, and this can involve future events. And obviously what is in the future is kind of imperfectly unknown. And also physical measurements that we've already made, because physical measurements are usually involving some different noise and things like this, and everything that we actually ignore also creates some uncertainty in our reasoning. It can be also coming from our modeling of the situation and how we treat what we observe, for example, and sometimes we might be ignorant of some things, or we have done some wrong modeling assumption and things like this. Uncertainty covers many fields, from physics to many things, but we are mostly taking account for uncertainty around statistics, because machine learning is mainly statistics, and around engineering, because we are producing systems that will be used in the real world, and this uncertainty quantification might be of primary importance here. So if we look at the traditional modeling system, where we have no uncertainty and everything is deterministic, so we basically will include in our models some rules about what we know from the world. And this could be some dynamics. Very simply, for example, the gravity will tell you what position at next time you can expect to have from the position at the current time. And a lot of laws in the physics give you relations between different values, and from this relation that holds almost everywhere, what you can do is to predict one value from the other, and so on. In practice, we'll have different things that make all our modeling actually uncertain, and some things that could be very difficult to tackle is the fact that actually the environment is non-deterministic. So for example, if I flip a coin, I don't know what will be the outcome, and I can model everything as well as I want. If I just know that somebody flips a coin, I cannot predict the outcome for sure, and this won't be solved by observing more information or things like this. Some sensors also give us some observation that could be partial or noisy, and this will lead to uncertainty in our modeling. We might also have limited data. For example, if I flip a coin only twice and I want to know if it's fair, then for sure I cannot really get much certainty about the fairness of the dice or of the coin if I have only 2 throws, because even if it's unfair or if it's fair, if I observe twice the same outcome, then I don't really know if it's fair or not. Also, everything about modeling that we do can create some uncertainty. So if we do some imprecise modeling or incomplete or wrong models, then we will need to add uncertainty in our model predictions. This is, for example, true with all the numerical simulations that we are doing, where it uses some numerical computations that are actually imprecise by design. It's usually categorized in 2 sections, two types of uncertainties. The aleatoric uncertainty that comes from randomness, basically, and when we talk about randomness here, it's inherent randomness of the phenomenon we are modeling, and this is the things that we cannot know. When I flip a coin, I cannot know the outcome, and so this is aleatoric uncertainty. Another class is epistemic uncertainty, and it's the thing that we could know if we model better or if we got more observations, more data. So here they are roughly categorized using color. So in green you will always have in this presentation aleatoric uncertainty, and in blue epistemic uncertainty. So as a second summary, aleatoric uncertainty is the true inherent randomness that lies in the phenomenon, and this has to be said, it's with respect to what we can actually observe, because when I flip a coin, for me it's actually random, so I cannot predict the outcome. But if I have all the physical parameters and all the details about the coin itself, then I can predict. But we are talking about, given our situation, so our things that we observe, what is actually inherently random. Said differently, no amount of additional data of observables that of the same kind that we already have can remove this uncertainty. What we have for epistemic uncertainty is basically when we lack training data, or when we made some wrong or simplified modeling assumption. So today's challenge is to discuss about these 2 uncertainty and to think about how to model them in machine learning and deep learning. One thing I won't talk in detail, but that is a field in itself, but that is involved in what we'll be doing anyway. It's what we call uncertainty propagation. So it's given a model that can be manually specified or already learned. How do we propagate the uncertainty from an input to the output? And so this will have to do with how the model actually transforms different kind of inputs, because if we're uncertain about the input, it's mostly the case that as if we had several different inputs. So here I will take a toy data set in 1D where we have 2 features, one feature, let's say X, and one predicted feature, Y. And here I will draw manually what aleatoric uncertainty is here and what epistemic uncertainty is. So what we will have, let me take this, okay. What we will have is that in this region for given X, we can have a lot of different Y values. So in this region here we'll have some kind of high aleatoric uncertainty. So we're doing regression, high aleatoric. And in the rest of this region here, we have rather low aleatoric. Why? Because for given X, we have really a small range of possible values. So there is no big ambiguity if we know the input about what will be the output. And this comes from data. It's totally independent from the model, basically. if I consider now more the epistemic uncertainty that comes from missing data or bad model, what we'll know is that where we have a lot of data here, we can model basically something like this. So here the epistemic uncertainty is quite low because we know pretty well what is the situation here. In this region it becomes high, like medium aleatoric epistemic uncertainty, because here if I had more data I would better know what happens, and here it's very high actually. And in the same way outside here it will be very high. And so a good model could become uncertain here and predict a wide range of things. So here we would be very low because there are a lot of data, and then maybe we will be very high here. Here very low still. And in between here we would like maybe that the uncertainty grows as we go far from the data. So here it would be a high aleatoric epistemic uncertainty. What can also cause epistemic uncertainty is if our modeling assumptions are wrong. And for example here, if I have a model that is unable to capture this sinusoid function here, and that's rather a model like this, here I will have some epistemic uncertainty. Epistemic coming from the model. So this gives you a kind of picture of these two types of uncertainty and where they are high and low. Basically, epistemic uncertainty is coming from missing data or wrong modeling, and aleatoric uncertainty comes from the inherent randomness of the thing. And yeah, just to come back to aleatoric uncertainty, here it's low because the true thing from the data we see from the data, even if our model cannot capture it, we see that it's very well defined what is the expected y given some x. But our model is wrong here. So we can do the same. So here it was 1D regression. Basically, we can do the same on this 2D data set for classification. So now we have two classes and we want to classify. And what we will do is to consider this example. And in this example, again, I will find the region of aleatoric uncertainty, so where there is inherent randomness. And inherent randomness in classification means that at a given location, we don't know for sure what are the classes. So here we'll have some huge aleatoric uncertainty. Similarly here, we can have some aleatoric uncertainty because in this region we're not so sure. I mean, it seems that there is not a clear-cut decision of what to do in this case for the two classes. In terms of epistemic uncertainty, it's basically everything that is outside of the data we observe that will be uncertain. So all this region here will be uncertain. So everywhere we don't observe things, and here we don't consider any model. I didn't draw any decision boundary, so it means that we won't consider the aleatoric, the epistemic uncertainty coming from the model. So I can try to plot this based on some estimation of the densities and stuff like this. So here I plot the aleatoric uncertainty that we see strong here and kind of strong here, even if it's low in some sense, because this could be some outliers and then there is no real uncertainty, it's just some input noise that creates this situation. For epistemic uncertainty, it's basically everything that is what we call out of the distribution, so out of distribution here. And as a quick summary, aleatoric uncertainty is in regions of class overlap for classification, and epistemic uncertainty is when we are out of distribution. This encompasses a lot of different situations in practice, and there will be some different solutions to this. But it's also important to understand that what we do out of distribution is kind of a decision that we have to make, and it might be that if we are close to some existing points, we will do a prediction based on these points, but as we go farther from these points, we should not trust our decision. And in practice, when you do machine learning, you always have a finite set of finite training set, so you're technically always on new points, so you're always kind of out of distribution. That's why the definition of out of distribution needs to be specified in the context of a given situation. So you have epistemic uncertainty in regions of low data also, and in this region of low data, so given that you have a finite set of a finite training set, it's possible that you also combine this uncertainty with some aleatoric source of uncertainties. And what I draw here is the previous examples, but I show you this kind of combination that I call aleo-epistemic uncertainty, and it's in regions where you don't have a lot of data, but it seems from the data that there is a possible a mixture of classes, for example. So these regions here, which you don't have a lot of data, but you have a good indication that the two classes overlap, will be what I call aleo-epistemic uncertainty. It's also true basically at all the boundaries of aleatoric uncertainty region. So you have a aleatoric uncertainty region here, the two classes, but just around this region, you don't have a lot of observations, but you may think that both classes are possible. So you find this kind of region of high uncertainty. And where you're in cases of imbalanced classification, for example, this region will have a high importance actually, because one class is not observed a lot, so you're in a case of epistemic uncertainty, and if there is an overlap, you have a merge with aleatoric uncertainty. So what we'll do now is come back to neural networks and to think about whether they can predict, not predict, but to give an estimate or an assessment of their uncertainty. And if you remember, a neural network is doing some activations, some products and activations between the different inputs. And at the end, there is a softmax, and what is predicted by a neural net that does classification is an output probability vector. So this seems to contain some information about uncertainty, or because it gives a probability for each class. The softmax is applied on what we call the logits, and we can see it as some log probability, and the output as some probability themselves. So the output is computed as each output is computed as the exponential of its corresponding logit, and then we normalize this exponential, so we divide by the sum. So you might say, okay, my neural net is predicting a probability vector, so it's good, and it can tell me, oh, I think it's half of a cat, half of a dog, and not a plane, for example. But in practice, we will see. We see that it's not exactly the case. So first, let's just think about something that outputs a probability vector. It's way better than just predicting a class. And if you compare, so this is classification, but if you compare with regression, in a traditional regression, for a given input, you predict a value. But this would correspond in a classification setting to predicting just one class. So when we predict an output vector, what we do actually compare, with respect to the equivalent regression, it's that we predict, let's say, a distribution. So for example, a mean and a variance on the output. So it seems to be better in terms of prediction to have a probability vector than just a value. And it's true, it's actually better. But with a probability vector, we cannot, for sure, distinguish aleatoric and epistemic uncertainty. So if I just, as a model, give you a probability vector, you cannot know if my doubt that I encode in the vector is actually coming from aleatoric or epistemic uncertainty. So a probability vector cannot convey properly this information, and I will take an example to illustrate this. Just a side note, sometimes it's sufficient to have this probability vector and you don't really care about the distinction between the two uncertainties, but most of the time you actually do for good decision making. So let's take an example where you have a model that is trained to distinguish two classes, let's say dogs and planes. I mean, distinguish dogs from planes. And you observe a new image, and the network predicts that it's 50-50 for a dog and a plane. So this can actually represent two situations. The example of this image, where you actually have a dog that is dressed as a plane, and this case here, where you have just a house, and there is no dog in this image, no plane. There are indications that there could be a dog because it's grass, and there could be a plane because there is some sky, but you have no dog or planes in this image. On the left, it's actually a green case where you have aleatoric uncertainty. So the model predicts 50-50 because it's sure that it's in between a dog and a plane, basically. That both answers could be meaningful. On the right, it's more epistemic uncertainty, where the model basically doesn't know. It's out of distribution, is very new, it doesn't know, it doesn't look like what it has seen before. So in both situations, it should answer 50-50 in some sense, which is good, but we don't distinguish by just looking at the probabilities here what is aleatoric and what is epistemic. So we will have to go further to actually be able to model this, and I'll come back more to this at the end of the talk. So this was a fake example, but if you take a true example, you can train a model on Cipher 10, which is basically something that will distinguish some dog, shoes, airplanes, birds, and things like this, and apply it on street view house numbers, which are basically the kind of image you have here that are small in this case to match the Cipher 10 task, but if you provide this image to the trained model, it will tell you that this is a dog with 100% probability. So the probability vector will be basically a 1 for the dog and 0 everywhere else. And similarly for the other images where this is a bird and this is an airplane. So deep models, and not only deep models actually, don't know what they don't know. So they are very bad at thinking about their aleatory, actually here in this case it's out of distribution, so it's some epistemic uncertainty, but it's also true for a region of inherent uncertainty, so for aleatoric uncertainty. So here it was for classification on images, but we can look at the boundaries on even simpler case, and we see here with a dataset with two classes, the two moons here, and what we see is the decision boundary, because actually we plot the confidence of the classifier. So it shows that it's confident everywhere except really at the boundary, but in most of the space it's very confident even out of distribution. So I give you the link to actually get more from this paper and the companion website. So now that I've introduced the different kinds of uncertainty in several examples and little different contexts, let's talk about how machine learning actually can handle this and what are the traditional approaches that we have. And also we'll see in deep learning how we do this, and then we'll discuss Bayesian networks. So one way of quantifying aleatoric uncertainty and improving the model in terms of aleatoric uncertainty is to really reason about what we call the calibration of a model. A calibration is for given, or for every x actually, to think about what the model predicts and what is actually the true situation. So basically to have a well-calibrated model, the two things should match. So the probability predicted by a model, so the probability vector that a model will predict for a given x, for a given image, for example, and the actual class probability. So the true class probability coming from the unknown data distribution that we are considering, that we call P of y given x here. So this is unknown, so actually what you do when you try to reason about calibration, what you have to do is to reason about what we call the expected calibration error. So it's an estimation from the data we have of the mismatch between f and p of y given x, the true that we don't have. So for this we need a lot of things, including like estimating the density of this from the dataset. So I won't detail this too much, how we can compute this, but if we want to actually compute it to optimize it or to improve it, we need to estimate it. So possible solutions to improve the calibration is traditionally basically to relearn part of the network. For example, you will fine-tune the network, especially the last layer that can be improved in some situations to fit some particular new data or some particular different balancing between classes and so on, and you will refit some distribution, some losses that are actually good for calibration, and this includes, for example, the logistic regression loss. Another solution is to fine-tune the softmax. So if a softmax doesn't have parameters, but to be able to fine-tune it, we'll actually add one parameter to the softmax. So instead of taking the exponential and dividing by the sum of the exponential, it will do exactly the same, but with a parameter t, which is the temperature. So before taking the exponential, it will divide by temperature. And the intuition is that if the temperature is 1, it's just a normal softmax. If the temperature increases, we will increase the predicted uncertainty. So we will make the vector that is the output predicted more uniform. And at the limit, if we tend to have t that goes to infinity, then all these values will be 0. So we'll get exponential of 0 for all the i's, and in the end, O, the output, will be uniform. So, and it's a continuum, because if you have 1, it's a traditional software max. If you have infinity, you always predict the uniform, so you're really doubting about everything. And if you predict 0, then you're actually having something that, not predict, but you use t equals 0, then you have a softmax that becomes a true max, so just taking the max value. Up to the fact that we take the exponential, but if we take the log behind, it's what it's doing here. So this was for aleatoric uncertainty, but if we think about out of distribution prediction, so for epistemic uncertainty, there is something I won't focus today, but it's a very wide domain of research. It's what we do when there is a dataset shift. So the target set is different from the training set. So we are basically out of distribution. So what I will draw is a small example. So what I will do is to imagine in 2D. In 2D we have a source dataset, which is a class here, and another class here. I do very simple situation, and we learn a separator, which would be something like this. And now what we will have is that I will duplicate this, because we'll have different situations and solutions. Oh, sorry. Okay. So what we have is a new dataset that arrives, and I will draw it in lighter colors. So let's imagine it's like this. And the blue, for example, the blue class in the new dataset, because, for example, the images are different, is like this. So we are really out of distribution. So what we observe is really different from what we had as input. And so this is what we call the dataset shift, basically. And we'll see a few solutions here. So this is the problem of what we call unsupervised domain adaptation, in the case where we have target data and we don't have any labels for this target data. So we don't know the classes of the target data, and we need to predict it. So here we don't know the color, basically, of the two blobs that we observe in what we call the target domain. So what we'll try usually to do is to reduce the discrepancy between the source and target datasets in terms of dataset distribution. And this is a natural fit for what we call optimal transport that tries to actually measure and reduce this discrepancy. So the first solution basically is to say, okay, I will redraw a similar situation here. So you observe points that are here and here. So everything that is on the wrong side of the classifier would be misclassified. But if I consider I try to map the two distributions, so the distribution of dark points with the distribution of light points together, then I will tend to move the green points here and to move the blue points here. And by doing so, I will tend to bring back the green point on the proper side of the decision boundary. So it's what actually happens in practice. This solution works. So the other solution is to say, okay, I have again my observations like here that are different, that are out of distribution. What I will do is use the uncertainty I know from the classifier. So the classifier is not just a classifier, it maybe tells me I'm uncertain here, something like this. And from this uncertainty, what I will do is to say that the points from the target dataset cannot be in region of uncertainty. So this point shouldn't be here, it will be pushed away from the boundary. But by pushing this point away, they will also pull the other ones because they are close to each other. And what we will do is to move basically everything that is on the boundary on the side that makes more sense. And it makes more sense because there are basically more mass on this side here. And so this is another way of doing this fixing of out of distribution due to that dataset shift. And this is done using the uncertainty information. So if this uncertainty information is not good, then it means applying this method will not work basically. And the better the uncertainty, the best this method will work. So this is all about domain adaptation and transfer learning. So it's a big domain, and I will not talk about it more today. A very general method for improving uncertainty quantification in machine learning is what we call ensemble methods. So the principle is very general, is to learn several models and to average their predictions. And the intuition is that by doing so, we will have basically models that are varied, and so they will not agree all the time. And when they don't agree, it's a sign that there is some uncertainty that is present in our data set, either aleatoric or epistemic actually. So the typical approach is what we call bagging, which is bootstrap aggregating. And the idea is to sample several datasets with replacement, which we call bootstrap actually, and to average the predictions. So the most well-known model today for this is called random forests, where you will learn several decision trees and aggregate their output. And what you do additionally in decision forest is what we call feature bagging. So you will actually also sample not only the dataset but the features. So it's different from what we call boosting, that I won't detail here, but as the terms are kind of similar when you don't know them, I wanted to insist on the difference here. So what I do now is that for different model in different slides, I will consider my dataset, a set of 20 or 25 models that have been learned. Here it's some linear logistic regression. I will always show 2 of such models to show that, for example, logistic regression captures some uncertainty in its modeling already. And so for example, here it's only linear separations and linear uncertainty regions. And I will show the bagging, so the aggregation of these 20 models. And we see that the decision is still linear, because if you aggregate some linear threshold, then you get some linear coefficient, you get something that is still linear. but the uncertainty region is better in some sense. It's much more refined, and it better actually corresponds to the data, because it's proved that bagging actually works for this. So I can take support vector machines, so it's also linear classifier in this case. So it's called SGD classifier because it's the scikit-learn name. But the difference is that it doesn't really assess its uncertainty, so it just gives you, it gives you a little more, but mainly gives you a decision boundary. But still, with such things that are certain, that don't quantify uncertainty, the bagging will actually have an uncertainty estimate, because the 20 model won't agree everywhere, and so this creates some actual uncertainty. And we see that we get something that is quite similar to logistic regression, for example. Slightly different still, but quite similar. In SVM and different models, you can actually do kernels, which means that you will create some fake features and then learn a traditional SVM. And if you do this with polynomial features, then with degree 3, then what you get is these separators here. And you see it's some examples here of separators that you get. And in the end, the boundary that you get around the data, inside the data, it's quite similar to what we got. It's slightly different, but now it can do some nonlinear things. And outside the data, it's actually predicting more uncertainty here, because the model and the features allow us to have a wider variety of things, and this translates into some better, because we're out of distribution, estimate of the uncertainty. So now we can do some deep learning, let's say, with 3 hidden layer multi-layer perceptrons, neural nets, and we see what they capture here. We can see 2 models here. Each individual model is actually capturing some uncertainty, and the bagging, so the aggregation of this 20 model, give us something like this, which is nice. It's not linear. It seems to be a good decision boundary. It quantifies some uncertainty, but still there are regions where it is actually certain, even though it's out of distribution. I've done the same with a very deep, for this test actually it's very deep, so 10 hidden layers perceptron, multi-layer perceptron, and what we see is that it's quite similar where we have data in this region here, but outside, given that the model is allows for more funky things, what we have is that there is a wider range of different predictions outside of the data. Actually, this translates somewhat in also some uncertainty estimate here in the bagging. So, as a summary for this on bagging, bagging nicely handles aleatoric uncertainty, because for all the things we've seen, the bagging is always very meaningful in region of aleatoric uncertainty. It predicts some uncertainty that is quite well calibrated actually. It works even if the base model is overconfident, and basically it's the sampling that creates some noise, some variety of models in the boundary regions. So the model family controls the bagging behavior out of distribution. So depending here on the models and features that we've selected, out of distribution we have possible higher uncertainty estimates or prediction, let's say, and basically if you take a simple model, out of distribution variety like linear model here will be low, so you will be overconfident in most of the regions where you should not be. If the model is complex, you will get something better, but still it's not very perfect from what we've seen. So it's not very perfect, and to be sure of this, we can actually take the same things here, so our dataset with the 3 blobs here, and zoom out. And if we zoom out here for 3 different models again with bagging, so we see that the dataset is here, for example, and we are certain here on these 2 regions that cover most of the space. Similarly, with some variations, but for for an SGD, so an SVM with a kernel, and similarly here for an MLP classifier, or even for the deep MLP classifier that has a wider uncertainty region, but still it's not perfect. What we would like to have is something like this, actually. So some certain decision around the points we observed, but as soon as we go too far from this point, then we are basically coming back to half-half as a prediction. So the gray region is half-half. And this doesn't mean that we cannot be very precise in region where we have data. So if we zoom back here, but we can also zoom back here and have something that is very precise, but still very uncertain around, I mean, when we are far from the data. So it's not like if we do one, we cannot do the other. It's just that most of the models actually don't try to handle this out of distribution uncertainty. So it's not the thing we will focus on right now, but there are solutions such as Gaussian processes that are models that handle this naturally. And another global approach is to say, okay, we will model as we've done here, but at the same time we will try to learn the distribution of points we observe so that we can know when we are out of the existing distribution. So it can be through this density estimation or what we call one-class classification, where you try to learn to distinguish between your data and novel data. Another solution is to say, okay, we'll generate random points everywhere in the space, and we will force the prediction of the network or the model to be actually uncertain, so to be half-half on these points that we generate randomly everywhere. So this works very well, but it can be costly to generate all these points actually. And it's kind of related to adversarial examples also in some way. So now we'll focus especially in deep learning, because what we've seen just before was generic methods for machine learning that can be applied on deep models for sure. But in practice, what we do in deep learning actually already contains some things about uncertainty quantification. So what we can do in deep learning, and that is actually done very much and works very well in practice, is to do ensembling on deep learning, but use the fact that we're doing a stochastic optimization to actually get several models by just reinitializing the stochastic optimization and redoing the optimization. So it will be costly because we'll have to run all the learning, the training process several times, and we'll have to save all the models. So if you have billions of parameters, it will be billions of bytes every time you save your model, so it can be costly also. So intuitively, if we have this loss landscape, so basically it's a plot where you show the parameters. So it's like the weight number 1, weight number 2, but it's actually 1 billion dimension space here. What you can do with stochastic gradient descent, so you start somewhere and you optimize your loss, your training loss, and you end up somewhere here after your initialization. But if you initialize somewhere else, like here, you will end up somewhere here, for example, and so on. But if you initialize several times, you will also discover some different modes, like here, and so on. So you will have models, like 1 model, 2 model, 3, 4, 5, 6 models here. If I initialize 6 times, you will have models that cover basically the different modes, so that are very different set of parameters. And by aggregating them, you will get basically a better model, because it will be better, especially at quantifying uncertainty, because it will be diverse in some sense. So this is basically what I call reseeding, so where you reinitialize your training process and do gradient descent again. You can do this also with different families of models, so you can try different architecture, because there is no reason to only use one architecture when you do this, or vary some hyperparameters, for example, even the learning rates of your optimizers and things like this. So in practice, if you take a simpler architecture, you will have less parameters for this architecture and also usually a simpler loss landscape. So you will average between different complexity of models, and you can also capture in this way uncertainty better. So this actually works very well. So ensemble of deep models are a very strong baseline for most of the problems. And it's basically a form of bagging in some sense, but you consider that stochastic gradient descent is doing the sampling of the dataset for you. One thing that we've seen in this summer school already also is dropout. So I remind here the dropout principle. So dropout can be applied either on weight or on nodes. So for this first example, I will just discuss with the nodes because it's simpler to represent. So if we have a network architecture like this and we decide to apply dropout, it means that every time we will be feeding an input and to have it processed by the network, and this includes every time we do the training, for example, we'll actually drop randomly some nodes. So for example, for one input, training input, we'll get this actual network because we dropped some nodes and we set everything to 0 related to these nodes. For another one, we would get this one, which is different, and so on and so on. So for every input, we can sample this differently. So dropout is basically equivalent to training 2 to the power of n models, because here we have n nodes, let's say, so we can drop them so they are either there or not there. So in the end, we have 2 to the power of n possible such situations, and the difference between just training to the power of n neural nets is that this is actually there are some constraints that this weight here is the same in all the 2 to the power of n networks. So there is a strong constraint here, but there is also an advantage is that we don't have to actually train to the power n times and to actually do store 2 to the power n situations also. So what we do in practice is that we actually sample randomly with some probability the fact that the node is kept or not. We can also do it on weights, so just dropping some edges here randomly. And usually at test time, when you do dropout, what you do at test time, you just use what we call the weight scaling rule at test time. So basically, if you had a dropout proportion of half, it means that every input here receives, in practice at training, half of what it would receive if all the nodes were here, in average. So what we do is that at test time, given that we'll have twice as many nodes that produce input for a given node, we will divide by 2 basically to actually compensate for this fact. So it's what we call the weight scaling rule. And we'll see that this is actually very bad because it means that at test time we lose our uncertainty, and even this doesn't work all the time properly because it's actually incorrect, even if it's a thing that is used. So dropout in practice should be applied at test time also, which can be a little costly because you have to sample different networks at test time for one single input. You have to pass it through different networks. So without going into the details, we might think about batch normalization also, that is a source of stochasticity. So in some sense, it's also a source of ensembling, as dropout is in our network. So it has interesting properties from this respect. And also just the fact, as I mentioned in the previous slide, that we do stochastic gradient descent with mini-batch, so by sampling data every time, is also a form of ensembling. If you want, the mini-batch is kind of bagging, and the dropout, where we select some weights only, is a kind of a feature bagging, not exactly features, but parameters bagging. So I will cover a small notion about what I call diverse or local ensembling, versus local ensembling. So when we do reseeding, what we've seen is that we will have models that are in different modes, and in Dropout we'll get mostly the same behavior, and we'll get an ensemble that is diverse, which is very good, especially when we try to estimate out of distribution uncertainty a little better. But there are also some, let's say, simpler approach that will focus on local diversity, so being better at exploring the diversity around a given model, where what we will do is to learn a single model and then locally estimate the distribution of models around this model. So let me draw an example. What we will do, for example, we will initialize our gradient descent somewhere and we will end up here. Or let's say, I don't know, let's say we'll end up here. So it's gradient descent, stochastic gradient descent, so we stop at some point, it's not necessarily at the optimal. And what it will do is to use the shape of, the local shape of the loss landscape. So basically it will try to use the local information, like the gradient and stuff, to actually estimate, so it will not be perfect, but to estimate a distribution around this model. So this, to estimate the loss landscape around this model. I remind you that here we are in a, 1 million dimensional space, for example. So it's not an easy task in itself. And from this estimation, what it will do is to draw. It will see it, let's say, as the Gaussian distribution, and it will draw some points. Drawing some points means what? It's drawing some weights, some weights for the network. So every point here is one neural net with different weights, but the same architecture. And it will use, we will use this ensemble here, that is not so diverse, but that well represents the loss landscape in this region, to actually do the prediction. And so this is what I call basically local ensembling, and this is the general process we can use. Now we'll see later that Bnns, Bayesian neural nets, are basically some kind of dense ensemble, so not just drawing some different models, but modeling a continuous distribution on models. And that depending on how we do it, they can be both local or diverse actually. So we'll now discuss especially about Bayesian neural networks with an introduction of what is the Bayesian approach actually before, which is the most interesting part, because Bayesian neural networks are mostly applying this approach to neural nets. So in a Bayesian approach, what you will do is to consider everything as random variables. So usually even your parameters are random variables, so you can reason about it. And you will use probabilities to do a lot of things. So let's focus on the only two rules of probabilities that exist, which are the product rule that tells you that the intersection of two events, A and B, so P of A and B, is equal to P of A given B times P of B. So basically it's the proportion of A inside B times the proportion of B in the universe, basically, and it gives you the proportion where you have both the two events at the same time. And you can write it in both directions. You can apply it in both directions. The other rule that is less important in our context, but that is the second important rule of probability, is the sum rule, that tells you that the probability of an event is actually the marginalization, so the sum over all possible situations, and we can take here all possible situations for another event of the joint probability between B, what we're interested in, and all the a given situation for a value of A. And we sum over all possible outcomes for A, and by doing this we have actually the probability of B. So the base rule that is used in Bayesian, in the Bayesian approach, is basically combining especially these two things here, And for now, it's very simple. It's P of A given B equals P of B given A times P of A divided by P of B. It's just rewriting the product rule slightly differently. We'll interpret this in the next slide. We can also combine it with the sum rule, and what we see is that it's basically P of B given A times P of A divided by the sum over all possible A's of the same thing. So this can be seen just as a normalization constant, and we compute the numerator and then we normalize by this. This normalization constant can be very intractable to compute actually, and this can be this is a huge problem in most of the Bayesian approaches. So everything like that is written here works with continuous random variable exactly in the same way. So in Bayesian learning, what you do is to use probabilities to represent all the non-deterministic stuff that you want to model, but also to represent uncertainty and any kind of uncertainty. So probabilities are a very good way of representing uncertainty and also reasoning about it. So the power of Bayesian learning is that everything is well formalized as probabilities, so reasoning about your data, your model, your uncertainty is all done in the same framework, which is the probability framework. So we'll take the base rule basically and consider the case where we have some parameters, for example the weights of a neural networks that I will call W here, and some data sets that I will call X, and that is basically the training inputs and the labels. So X contains everything here. So this is the base rule. And what I told you is that this P of X here is actually something that we can consider as a normalization constant. So often you will see that people write it as P of W given X is proportional to the numerator, in the sense that it's the numerator times a constant. I rewrote it differently to introduce, to make things clearer, even if it's more verbose. And what we are actually interested in P of W given X, the probability of the weight given the train set, and this we call the posterior. And we call it posterior because it's basically the probability distribution over the parameters, the weights, given the training set. Or it's what we know about the parameters after seeing the training set. And that's what it's called the posterior distribution. And the base rule tells us that this posterior distribution is actually the probability of the training set given the weight, and this is what we usually call the likelihood, times the probability of the weight given nothing. So this is what we have as a prior on the weight. So if we don't know anything about the weight, what is our distribution on this weight, our belief on this weight, and divided by the probability of the training set given nothing. So here it's something that is constant if we have a fixed training set. So if our goal is to model what we know about the weights, this is actually constant, and that's why we use this proportional here, because we can simplify in some sense if we don't care about the actual value of probability, but if we're okay with having the value up to constant, it's okay. So if we apply this to Bayesian to neural networks, so it's principle of Bayesian neural networks. What we have is that we consider a simple network here, the same that we had before, for example, and we have weights. So it's a traditional neural network. But what we can do is to apply a Bayesian approach to this. So it means that every weight will become a distribution, and this will be true for every weight in the network. So in the end, what we will do in a Bayesian approach for neural nets is to model every weight as a distribution. So what we can typically do, and we'll see that we can do something else later, is that we can consider that each weight is modeled by a distribution, and that this distribution will be, let's say, a 1D normal distribution, and it will be with one mean and one variance. So we have one mean and one variance for every weight here. So if you have a neural net with 1 billion weights, for example, then it means you will have to optimize 2 billion parameters to find 2 billion parameters. It's a lot, but it's just twice more, and it allows us to model uncertainty about this model, the weights, basically. So we'll quickly, because this could take forever to actually do properly, we'll quickly see that how we optimize actually, how we can optimize Bayesian neural nets. So I remind you that the goal is to find the posterior distribution, which is basically the likelihood that we usually know how to compute, times the prior that we need to specify. In the Bayesian framework, also when you have to predict, given a learned Bayesian neural net, what we call the prediction using the posterior, which will be actually the prediction given some weights, and it will be weighted by the quality of the weight according to the posterior. So basically, if we have a distribution on the weights, to actually do a prediction, we should integrate over all possible values of weight according to our distribution and average the predictions that a given network with these given weights would give us. So variational inference or stochastic gradient variational base acts as follows. So we will parameterize the posterior, as I mentioned before. So for example, some normal distribution for each weight. So 1 billion means and 1 billion variance in the same example of a 1 billion parameter neural net. We'll do stochastic gradient descent on these parameters. And when we need to do a forward pass, so to take an input and to forward it, being it at training time or test time, but here especially at training time, we will approximate this prediction, that is what we should optimize, by a single sample. So this is an integral, so instead of computing the full integral, which is impossible to compute, we'll actually draw a single sample to actually learn. So we'll draw one sample from the posterior, and then we will use the prediction from this sample to actually do the inference. To do the forward pass, basically. So in this school, you have seen autoencoders also, and you will manipulate variational autoencoders. Without diving into the detail, just to make a link between BNN and VAE, because both use variational inference. In VAE, you have two tricks for optimizing VAE. One is the reparameterization trick that will reformulate some things where we sample, like sampling the weights from a normal distribution, as a different way of sampling, so that actually the gradient in the gradient descent process can actually flow down to the parameters. So here it's not W, it's mu actually, so down to the parameters. So this reparameterization trick will also use it while training BNNs. It's everywhere as soon as you do stochastic optimization with gradient descent. In VAE, we also use something called amortization, and this will not be possible actually in BNNs. So it's due to the fact that in VAE, what we are treating in the Bayesian manner are the latent variables, and these are specific, dependent on the data. Well, here our parameters are general and independent. Not independent, but they don't depend on every individual point of the data set. One thing that we'll now see before closing is variational dropout. So how dropout can actually be seen and modified to be seen as a Bayesian approach. So in traditional dropout, what you do is you take a probability of dropping, which we call 1 minus p here, and you keep the weight with probability p, and if you, with probability 1 minus p, you set it to 0, if it's weight dropout. So the interpretation as a Bayesian this Bayesian approach is that the weight is actually drawn from a mixture with probability p, a mixture between the value 0 and the value vi, which is the actual parameter that we are trying to learn, and the actual weight is either 0 or vi, the weight number I. We can also reparameterize it if we want, and it's where you have the reparameterization trick also. And the implication when you treat it Bayesianly is that you should apply dropout at test time, because as we've seen before, the prediction should be the integral of the predictions according to the posterior, which can be seen. So this is totally equivalent to seeing it as an expectation under the posterior of the prediction. And this expectation or integral can be approximated with samples, by drawing some different samples from the posterior and averaging the predictions from these samples. So this is one neural net with some fixed weights, and these weights have been drawn from the posterior that we inferred from the data, the training set. This is the reparameterized version, but it's not different. It's really we average the decision from different models. And this means that if we want to do proper prediction in a Bayesian context, we have to apply dropouts and to sample different dropouts for every input at test time. And this is often called Monte Carlo dropout. So this applying dropout at test time. When you do Bayesian treatment of dropout, in addition to having to apply it at test time, knowing that now in a Bayesian world everything can be a random variable, you can also treat p, so the probability of dropping, as a random variable. And so basically to infer or to learn the values that you should use for p. But if you start to have p that can move, then what you should do is to consider that as p moves, you should decide whether you have a single p that will control the dropout on the whole network, or a p per layer, or a p per weight, for example. And all these situations are meaningful, actually. What you will do if p becomes a parameter, it means that when you will do learning, you will work on both the weights and p. And what you will try to infer is the p of theta, so the weights and the dropout probabilities, given the training sets. And so, without going into detail, you will need a prior on this small p. And this prior basically will act as a natural regularization. So what you will have is that when training, which is non-trivial by the way, you will infer the best dropout probability p, best in terms of fitting the training set and in terms of generalization, so kind of out of distribution, the generalization also. So there are different variations of dropouts, and most of them can be seen as Bayesian things. And by playing with the prior on the dropout probability, you can actually ensure or encourage the network to make a sparse decision. So in the sense that it will tend to drop some weight systematically. So it will basically remove some weights from the network, and this can learn some naturally compact models. So here I put a reference to some interesting paper on this, quite recent, and that will discuss different things around this. So a small summary of Bnns. You consider each weight as a random variable, you formulate the prior on the weights, you observe some training data to infer the posterior knowledge on the weights, and then you use this for prediction, for example by using dropout at test time in the example of dropout, or by sampling at test time. So Bnns includes a lot of variations of dropouts, and this simple example where we consider that the weights are normally distributing and we model them with a mean and a variance, for example. The inference, the learning and everything is done usually using stochastic gradient descent on what we call the variational parameters, so the thing that control the distribution on the weights. We use sampling at test time usually to make predictions that include a good uncertainty assessment. So for the sake of time, I will be fast on this section. So just to show you that these are actually used in practice, so this paper is quite interesting because it considers chest X-ray images, I guess, and they try to estimate the prediction uncertainty also. I mean, not to estimate it, but to predict from the model. And they show that with a drop weight on the convolutional neural net, they improve classification and they have a good quantification of uncertainty, which is very important when you combine model decision and expert decision. Here in this paper, they compare, for example, different approach, so drop all, drop last, and so on, to model uncertainty about the prediction, and a normal model has no uncertainty estimate for its own prediction, but with different methods you can estimate also when you're uncertain. So a model can say, okay, I predict this, but I'm not totally sure. In the same paper, they also showed that you can recalibrate models, and I don't detail this, but recalibration means that you're closer to the diagonal after recalibration, and what we see is that it works in some sense in this context, but there are still some miscalibration even after recalibration. Another paper or set of papers that actually show that by better modeling uncertainty, you can actually improve classification accuracy in some multi-step process where you use UNets and things like this, or ResNets, to actually do inference of both some classification and uncertainty, and use this to make a better prediction. So some openings, I mentioned Gaussian process. It's basically an infinitely wide Bayesian neural network, so as if every layer in your Bayesian neural network was infinitely wide with infinite number of neurons. It's a good kind of model because it's well formalized in terms of probabilistic framework. It has closed form solution, so it can be very efficient unless you have too much data, but there are a lot of works around scaling these models properly. Given it's a probabilistic model, it can learn its prior, in some sense learn its prior easily, and for example, it can learn that some data that we observe in this region here are periodic, and predict properly in the future some periodicity like this, which is quite nice for temporal data, for example, and this can be done automatically. So it's a sound probabilistic model, so it can be easily combined with other probabilistic models that exist and that are plentiful. We can also do deep Gaussian processes to avoid one thing that we have to specify with Gaussian processes, and basically it looks like a neural net, but every node is a Gaussian process, so it's much more complex and it can do much more things. I give just you some examples where people apply Gaussian processes to reconstruct tomographic images or equivalent things. One last thing I want to mention is that sometimes people think that probabilities are not sufficient to actually model uncertainty properly. So sometimes we want to actually explicitly represent the confidence, let's say the epistemic uncertainty in some sense, that we have about a given belief, which would be a kind of aleatoric uncertainty. So there are different frameworks to think about this. One that I want to mention is the evidential framework and evidential deep learning, which is a kind of a hype today, where instead of predicting the parameters of an aleatoric distribution, in the sense that, for example, if you do regression, instead of predicting the parameters of a Gaussian distribution on your target prediction, or if you do classification instead of predicting a probability vector, what you will do is predict a distribution over these parameters, so the parameters of a distribution. So it's like some meta parameters that you predict. So it can be seen as a way of representing epistemic uncertainty on top of aleatoric uncertainty. So if I take from this deep evidential regression paper an example, so if you predict a value y, when you predict aleatoric uncertainty, you will predict a distribution on Y. But what you do actually in evidential deep learning is that you don't predict just a distribution on Y, you predict this thing here, which is a distribution on distributions on Y. And this could be, can be actually parameterized in this case with 4 parameters. So what your neural net will predict for every input point is 4 values that control this distribution, that is itself a distribution on the parameters of distributions on your observable. So here it's a kind of modeling of the aleatoric uncertainty, and here it's a modeling on top of this about your belief about these different situations of aleatoric uncertainty. So this two-level thing allows you and allows the model especially to learn to predict its own confidence on its belief. So I don't detail this much more, but it's very interesting, and it's kind of minimal in the changes you have to do in your architectures. So for the sake of time, I will stop here. You will find online the slides with updated and fixed typos and things like this, and updated things. I will take your question now, and I will update the slides with possible answers to this. So thank you, and see you soon.